Hello, this is the section 16.2 to 16.4 lesson on the topics of basic counting principles and the multiplication rule. In this lesson, we're going to take some ideas from section 16.1 and combine them with some new ideas that we call counting principles in order to calculate some basic probabilities. Well, one of the key ideas from section 16.1 was this Rule 2 or theoretical approach for calculating probabilities. So if we have an experiment where all the outcomes are equally likely, then we can calculate the exact theoretical probability of some event by dividing the number of ways the event can occur by the total number of possible outcomes. And so in order to apply this Rule 2, we don't need to list all the possible outcomes. All we really need to do is count the number of ways that things can occur. And then we divide and we're all done. And so that kind of motivates this idea of counting principles. We're going to talk about how we can count the number of ways that the event can occur and count the total number of possible outcomes without actually having to list everything out. Now, before we do that, we need some definitions. So section 16.1, we introduce these two definitions of an experiment and an outcome. An experiment is some activity in which the result is unknown until it's performed, and an outcome So let's do an example of a multi-stage experiment. Let's suppose that we spin a spinner and then we roll a die, or as the book calls it, a number cube. And I honestly don't know why they call it a number cube rather than a die, but whatever. So this little diagram here illustrates all the possible outcomes. This is what we call a tree diagram. So it shows we start here with really nothing, and then we spin the spinner and we get either red, a blue, a yellow, or a green. And then we roll the die and we get either a 1, 2, 3, 4, 5, or 6, and a 1, 2, 3, 4, 5, or 6, and so on and so forth. And then here that they list the associated outcome. So one outcome is that we get a red and then a 1. Another is that we get a red and a 2. Here's another one, a blue and a 4, and that lists all of our possible outcomes. Now, drawing a tree diagram like that is a little cumbersome, but fortunately we don't have to do that in every problem. Let's illustrate another example of a three-stage experiment where we're going to flip a penny and then a nickel and then a dime. And here's a tree diagram of all of our possible outcomes. So with penny, it's either heads or tails. Nickel, it's either heads or tails. Dime, it's either heads or tails. And then, for instance, this first outcome is heads, 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 or written as just HHH. The next one would be heads, heads, tails, HH, tails, and so on and so forth. So there's all of our possible outcomes. Now, we could count those, and we'd see there's 8 different outcomes. But here in a bit we'll see a little bit simpler way of counting those outcomes than having to list all of them with a tree diagram like this. So let's go back to this first two-stage experiment and let's count the number of outcomes without actually having to list all of them. So from this tree diagram we see that from this red outcome we have 6 different possible outcomes. From this blue outcome we have a total of 6. From this yellow we got 6, from the green we've got 6. So this illustrates that here we've got 4 groups of 6 different ordered pairs, or that's just another name for our outcomes. So 4 groups of 6, well that sounds just like our definition of multiplication. So the total number of outcomes is just the 4 groups times the 6 items in each group, 4 times 6, which is of course 24. So we can easily So let's kind of generalize this observation in what we call the fundamental counting rule or the fundamental counting principle. And this is something that's actually easier to do than it is to say. Here's what it looks like in words. If the first sub-experiment has m outcomes and the second has n outcomes, then the total number of outcomes in some multi-stage experiment is m times n. So you just multiply the number of outcomes in the first experiment times the second, and that gives us our total number of outcomes in the overall multi-stage experiment. So let's go back to this example and just kind of show an easier way of applying this fundamental counting rule that doesn't require us to list all of these possibilities. So the way I like to do this is to start off by drawing two blanks and label the first blank as the first sub-experiment, the second as the second sub-experiment. So we got the spinner and the die. And then I ask myself, well, how many possible outcomes are there from the spinner? Well, obviously there's 4. So we draw 4 in that blank. And then ask the same question about the second sub-experiment. And there's 6 possible outcomes from that die. And then the fundamental counting rule says we just multiply those and we get 24. So that's how we can apply this fundamental counting rule without having to draw a tree diagram and list all of our possible outcomes. Now let's apply this fundamental counting rule to our 3-stage experiment. So we draw one blank for each stage, the penny, the nickel, and the dime. And I say, well, there's 2 outcomes from the penny, there's 2 outcomes from the nickel, 2 from the dime. I multiply them and I get 8. And so this fundamental counting rule applies to more than just 2-stage experiments. We can apply it to any number of stages. So there's 8 possible outcomes. We might also call this the number of combinations. So we'll kind of use number of outcomes and number of combinations interchangeably. There is a technical difference between them, but we won't get that in depth here. So number of combinations is the same as the number of outcomes. Let's apply this to another experiment. This one's a little more complicated. In a certain state, license plates currently consist of 2 letters followed by 3 digits. If the letters and digits can be repeated, how many such license plates are possible? And so selecting a license plate here is an experiment. I don't know what's going to happen until I actually do it. So the question is, how many different outcomes or how many different possible combinations are there? So when I select a license plate, I've got to choose the first letter, the second letter, and then the first digit, the second digit, and the third digit. So I ask myself, well, for the first letter, how many different possibilities are there? Well, there's 26 different letters. Now I ask myself, same question for the second letter. Well, the letters can be repeated. So if my first letter is an A, the second letter could also be an A. So there's still 26 letters to choose from. Now my first digits, well, that can be anywhere from 0 to 9. So there's 10 different digits. The second digit, again, I can repeat that first digit. So if the first digit were a 5, the second could also be a 5. So I've still got 10 digits to choose from. Same from the third. And so now I just multiply those and I do that arithmetic. I get 676,000. So there are 676,000 different combinations of license plates that are possible. Now let's use this example to calculate a probability. So let's suppose that we live in this state and we might ask, what's the probability that someone guesses your license plate? Well, according to Rule 2, the probability of getting a correct guess is equal to the number of correct guesses, that's the number of ways that this event can occur, divided by the number of possible guesses. Well, in the previous example, we just calculated this denominator. We know how many different license plates are possible. And then the number of correct guesses, well, you've only got one license plate, so there's only one correct guess. So we take the one correct guess divided by our 676,000 possible guesses, and we do that arithmetic, and we get a very, very small probability. So not very likely that someone's going to guess your license plate correctly. Now let's look at a slight variation on this same problem. Suppose we got the same situation, however, the letters and digits cannot be repeated. So that means if my first letter is an A, then the second letter can't be an A. I've got fewer possible letters. So we're going to start off with our same 5 blanks. We got 2 letters followed by 3 digits. So I say, well, for the first letter, I've got 26 choices. But now the second letter, once I've chosen that first letter, I've reduced the number of letters that I Now let's talk about a difference between this first example where things can be repeated and the second where things cannot be repeated. When they can be repeated, as in that first example, the sub-experiments are said to be independent. So that means that one does not affect the other. So when I selected my first letter, that does not affect the number of possibilities for my second letter. Same for the digits. Now, in the second example, where things cannot be repeated, the sub-experiments are said to be dependent. And that's just the opposite of independent. So dependent means that one does affect the other. Once I selected my first letter, that affects the possible choices for my second letter. So things are said to be dependent. Let's do another example dealing with selecting an outfit. So Fred has 3 shirts, red, blue, and green, and 2 pairs of pants, black and khaki. If he randomly chooses a shirt and a pair of pants, find the probability that he chooses a red shirt and a black pair of pants. So first we need to determine how many different possibilities are there for this multi-stage experiment. So the first stage consists of selecting a shirt. The second consists of a pair of pants. So we say, well, we got 3 colors of shirts, 2 colors of pants, multiply them, and we get 6 possible outfits. So now the question is, what's the probability that he gets a red shirt and a black pair of pants? Well, we can use Rule 2 and say, well, there's only one way that he can get a red shirt and a black pair of pants. Out of 6 possibilities, everything's equally likely, so by Rule 2, this probability is 1/6. Well, now let's make an observation here. The 6 was calculated by taking 3 times 2, and by multiplication of fractions I can break this up as 1/3 times 1/2. Now what's significant about that is that 1/3 is the probability of getting a red shirt, because there was 1 red shirt out of 3 possibilities, and 1/2 was the probability of getting black pants, because there's 2 pairs of pants and one of them is black. So what I've got here in the end is a probability of kind of one thing happening and a second thing happening, and in the end we can calculate that by taking the probability of the first thing times the probability of the second thing. So let's kind of generalize this in what we call the multiplication rule, which says that in a 2-stage experiment where the sub-experiments are independent, the probability of getting event A in the first stage and event B in the second is denoted the probability of A and B, and we can calculate it by taking the probability of A times the probability of B. So that's just exactly what we had in this example. We had a two-stage experiment. Things were independent because my choice of shirt did not affect the choice of pants. And I want to know the probability of one event and a second. In the end, I multiplied. So kind of three important words here are independent. You got to have independent experiments. The word and then multiplication. So think of and is associated with multiplication as long as things are independent. So let's apply this to a simple example. This is a little game of chance that's described in the book. So we've got here a duck pond with some rubber ducks floating around. One of those rubber ducks is marked with an X and the other four are marked with O's. And then we got a frog pond here with rubber frogs floating around. One of them is marked with O and the other three are marked with X. And the game is won. So you pick a duck and then you pick a frog. And the game is won if both the frog and the duck are marked with an O. Find the probability of winning. So we want to know the probability of winning. And one general approach for solving probability problems is to start off by writing down what it is we're trying to find. We want to know the probability of winning. And then we want to restate that in terms that we know how to work with, namely the word and. So winning means I get a duck with an O and a frog with the O. So now I see the word and, that makes me think multiplication rule. So then I check, are things independent? Well, what I choose from the duck pond does not affect the frog pond because they're completely separate ponds, so they're independent. So by my multiplication rule, I can take the probability of an O duck times the probability of an O frog and multiply them. So now I need to calculate these individual probabilities. Well, probability of getting an O duck is easy. I've got 5 ducks to choose from. 4 of them are O's. So this probability is 4/5. Likewise, out of the frog, there's 4 frogs. One of them is marked with an O. And so that probability is 1/4. So we take 4/5 times 1/4. And that multiplication is easy to do. It's 1/5, which as a decimal is 0.2. So we got a 20% chance of winning this game. Let's our last example. Let's look at this 3-stage experiment of flipping a penny and then a nickel and then a dime. And we might ask, what's the probability of getting a tail and then a tail and then a heads? Well, there's a couple of ways we could do this. Number one, we could say, well, there's only one outcome in which I get tails, tails, heads out of 8 possible outcomes. And so the answer is 1/8. But let's look at how we could calculate that without actually having to count anything. So I might say, well, tails, tails, heads means that I get a tail and then a tail and then a heads. So I see the word and I check, are things independent? Well, what happens to my penny has no effect on the nickel, has no effect on the dime. So things are independent. So I apply my multiplication rule. Take the probability of tail times the probability of tail times the probability of heads. And then each one of those is 1/2. Because on the penny, I got 2 outcomes. Each one is equally likely. Same for the nickel, same for the dime. And then I just do that multiplication. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. I get 1/8. So there's my probability of getting tails, tails, heads. That didn't involve listing my outcomes or even really counting my outcomes. It was just break it down, use the multiplication principle, and we're all done. So that's it for this lesson. The assignment is to read section 16.2 to 16.4 from the textbook.